problem, we are asked to verify that Rolle's theorem is applicable and also find C that is guaranteed by Rolle's theorem. And remember, there are three conditions or hypotheses for Rolle's theorem. F continuous on the interval 0, 9, and I will continue writing as a difference. It's a difference as the difference of two continuous functions on that interval. The square root is continuous between 0 and 9, and 1/3 x is a linear function, continuous everywhere. And therefore, I'm quoting a theorem that says if two functions are continuous, their difference will be also continuous. Then for the same reason, I will say f differentiable on the open interval 0, 9 for the same reason, because this function is a difference of two functions that are differentiable on 0, 9. Open, because I know the square root of x is not differentiable at 0. And the last condition I have to check that f of 0 equals f of 9. If f of 0 does not equal f of 9, Rolle's theorem is not applicable in this case. So when I try to find f of 0, that is 0. When I try to find f of 9, I have 3 minus 3 is 0. So all three conditions are fulfilled. Then we'll say there exists, so therefore there exists by Rolle's theorem a C in the interval 0, 9 such that f prime of C is 0. In other words, if a function continuous and differentiable starts at one point and it comes back to the same height, it must have a turn somewhere. That's all it means. But a turn in terms of the derivative, it means f prime is 0 there. So I have to find f prime of x, which is 1 over 2 the square root of x minus 1/3. And I have to set 1 over 2 the square root of c minus 1/3, set it equal to 0. Because that's what I have to show, that c exists, and c must be a number between 0 and 9. So I move 1/3 to the other side. 1 over 2 the square root of c equals 1/3. I cross multiply, and I get 2 the square root of c equals 3, or the square root of c equals 3/2. And this now is a radical equation, and I have to square both sides. So c equals 9/4. And c equals 9/4 is guaranteed to be a number between 0 and 9. And this is all guaranteed by Rolle's theorem. So if the three conditions in Rolle's theorem are fulfilled, then C must exist, at least one. If you remember, we can have as many. We don't know, but at least one will be there. Any questions on Rolle's theorem? Is that okay? Now let's look at the mean value theorem. Let's look at natural log. So this is problem 11 on to 89. So we have f of x equals natural log x on the interval 1, 4. The mean value theorem is more relaxed. It only has two conditions. I only have to show, number one, and say that f is continuous on 1, 4. I know it's continuous because I know its graph. So this is 1 and this is 4. Function is continuous on 1, 4 because that's the graph of natural log. Number two, f is differentiable on the open interval 1, 4 for the same reason. It's a function that we have a theorem that says any log function, any rational function is continuous where it's defined, and it's differentiable on all its domain. So for the same reason, and I have to state something like that. Then the mean value theorem guarantees a C in the open interval 1, 4. But now this gives us f prime of C equals f of B minus f of A over B minus A, where A is 1 B is 4. So in order to create this equation, first I have to find f prime of x, which we know is 1 over x. So then 1 over c will equal f of b, which is natural log 4, minus natural log 1, which is 0, over 4 minus 1. Correct. So that would be 1 over c equals natural log 4 over 3. I flip both sides, so c equals 3 over natural log 4. And this number better be between 1 and 4.
Can you explain the 1 over c again?
Yes. F prime of c.
Yeah.
This is f prime. I just plugged in c in it, and I got 1 over c.
Okay. Oh, okay. Sorry.
No problem. So I check, just to make sure. I put in 3, and I divide by natural log 4. And this better be a number between 1 and 4, and it is 2. I got 2.16. Okay, so these are the role and mean value theorem. The rest is all about graphing. I still would like to show a graph with a slant asymptote. Okay, would you like to, are we okay with Newton's method? Yes? With Newton's method? Yes. Okay, just any example, quickly. 21? Okay. Can you give me the example? That's it? Okay, very good. So then I have x cubed minus arc tangent x equals 0. So our function is x cubed minus arc tangent x. I have to create that big function, which is x minus x cubed minus arc tangent x, everything over 3x squared, minus 1 divided by 1 plus x squared. So in the graphing calculator, I have to put in the original function because I have to have an interval. I don't know where to start. So I have x cubed, and then minus tangent inverse of x. And I go back to the table, and I plug in some numbers. 0. I already found the solution, but I can't use it. 2, 3, okay, -1, okay. I can't use that either yet. So I already found the solution, which is 0. Okay, I still have to find another. I can't. Say it again. Any questions? Okay, so if that is, so I'm looking here, let me use the standard viewing windows. Just look at the graph for a second. Okay, so I see the solutions are roughly -1, 0, and 1. Is that true? Okay, so there is a solution between 0 and 1 because it's not at 1. Okay, I'm going to put in 0.5. 0.5 is a negative number. No, I didn't put 0.5. 0.5 is negative, and at 1 is positive. So I know there is a solution between between 0.5 and 1 because it changes sign. Okay, so my interval that I'm using is 0.5 comma 1. There is a solution between 0.5 and 1. And we have to decide which one will be our initial value. I'm checking when I plug in 1, this is 3, and this is negative 1/2. This is not 0. I can start with 1. Okay? Is that clear? Yes?
So I have a question about that. The way I had seen it done before in the book was that they graph both functions, look where they intersect, and then pick that as their x sub 0. Is that okay to do as well?
Yes, but you cannot use that in Newton's method. You have to create the function for the Newton's method.
I mean to give you your start.
Yeah, you can use the intermediate value theorem the way you like.
Okay.
It doesn't matter. You can graph two functions and see where they intersect. Or you can graph one and see where the graph intersects the x-axis, which is the same thing.
Okay.
So you're using these two functions to find the intersect, and I'm using this function and this function to find the intercept.
Okay.
It's the same thing. They will cross at the same point.
Got it.
Very good point you're making. But careful, because if you don't create the function, you may get confused in what to put in Newton's method.
Yeah.
So that's why I create the function from the beginning, and this is the function I'm using for the top, and this is the derivative that I'm using for the bottom.
Well, yeah, I mean, you need both to look at where they intersect anyway, so creating the functions.
But creating the function means you have to have 0 on one side.
Yes.
Okay.
Yeah.
As long as you are okay with that, that's fine.
Yep.
Good. So now I'm back. So in y equals, I have x minus the function. That's my function, x cubed minus tangent inverse, and parenthesis divided by, in parentheses, 3x squared minus, in parentheses, be very careful with this, 1 divided by, in parentheses again, 1 plus x squared. Close the parenthesis for the denominator, close the parenthesis for the denominator, for the fraction, and then I need one more. Okay, so now I go to get out of there, and I want the variable, and I go to the variable, and this is of 1, and I get 0.91. This is my x1, and then I copy and I plug in the previous answer, and then I plug in the previous answer. So it depends on where I want to stop. If I have 5 digits, and then if I have 3 digits, I can already stop. Now I thought that this was already clear since yesterday. What do you think is still the problem? I'm sorry? Okay, very good. Other questions, and you have to write down those x1, x2, x3, and show where you stop. Is this okay? Okay. I'm sorry? No, it will say in the problem. 4 digits, 5 digits, whatever. Yeah. Good. What was I doing next? What did we say we were doing next?
Slant Asymptote.
Okay. So we are okay with Newton's method, graphing, right? Rolle's theorem, mean value theorem, and L'Hopital's rule, limits, right? Are we okay with that? Okay. We didn't finish the one from yesterday. And I don't remember where we stopped. Do you have it?
You basically finished the last part of that. Yeah.
So we were supposed to differentiate that. So please, this is a very important type of problem. We did like 4 or 5 problems like that. So please go back and review those. What else? And slant asymptote and optimization. So do you want me to finish that problem, or you want me to show a slant asymptote now?
Slant Asymptote.
Are you going to be okay with that particular problem? The one that we didn't finish last night?
That was the x over 1 x squared.
Say it again.
Is that the x over 1 minus x squared?
No, I'm talking about the limit. The limit we did not finish. The one with the natural log that we had to, something tangent raised to cosine or something, I don't remember. That one we didn't finish. Okay, let's look at a, remind me, okay? Let's look at a slant asymptote now, okay? So let's say f of x equals x cubed minus 1 divided by x squared. Because the degree of the top is exactly 1 unit bigger than the degree of the bottom, this function will not have a horizontal asymptote, but will have a slant asymptote. I don't know if it's this way or this way, but a slant asymptote. So let's start with a chart. What is the domain of this function? Yes? If you remember how to factor this, you will factor into x minus 1 and x squared plus x plus 1. The formula is in the front cover of your book or back cover of your book, something like that. And then you will realize that this function is 0 at 1. Also, this function can be rewritten as x cubed over x squared minus 1 over x squared. And this is very important because I'll simplify and I get x minus 1 over x squared. Just the quotient of this division, x equals y, or I should say y equals x, is the slant asymptote. So the quotient of this division, just the quotient, is always the slant asymptote. Now, how do I graph y equals x? Does it have a positive slope? Or does it have a negative slope? If it has a positive slope, the function will follow the asymptote. So the limit at negative infinity will be negative infinity, and the limit at positive infinity will be positive infinity. Correct. But I have to write that. But it's easier if you apply the limit to this. So the limit of x minus 1 over x squared as x approaches infinity, and the limit as x goes to negative infinity of x minus 1 over x squared. Where does this go? Just this piece. When x approaches infinity or negative infinity, where will this piece go?
0.
Exactly. So that's why this will go where? And this will go? Exactly. So that's how we get positive here. I meant negative here and positive here. Y equals x slant asymptote.
I thought we had to divide them into each other.
I did. Because the denominator, you're right, because the denominator I chose had only one term, it was easier to separate it.
Okay.
There is no need for long division if the denominator is just one term.
Okay.
If I had here x minus 1, then I would have had to use the long division or synthetic division. Correct. Good. So now the limit left-hand side and right-hand side of 0. I'm going to use this for the limit left and right of 0. So limit as x approaches 0 from the left, from x cubed minus 1 over x squared. 0 from the left is negative over 0. So 0 from the left is negative 0.1. Negative 0.1 cubed minus 1 is negative. Negative 0.1 cubed squared is positive, so this is negative infinity. Now on the other side, limit as x approaches 0 from the right, from x cubed minus 1 over x squared. The top is still negative, the bottom is still 0, and 0 from the right, 0.1, still negative, 0.1 squared, positive, both sides the same thing. And this implies that x equals 0 is a VA. So negative, negative. I'll write myself a note, y equals x slant asymptote, x equals 0, vertical asymptote. There is nothing else I can find about the function from the function itself. So now I'm going to differentiate, but I like to differentiate this, not that. So let's find f prime, and I'm differentiating x minus x to negative 2, which is 1 minus, with minus 2, positive 2 times x to negative 3. And this is 1 plus 2 over x to the third, or x to the third plus 2 over x to the third. Yes, it's ugly. When I set it equal to 0, I have x to the third equals negative 2. And that's the only real solution. So I have to take the cube root. I don't know what the cube root is of negative 2. So negative 2 raised to power 1 divided by 3. It's negative 1.3. So x approximately negative 1.3. Negative 1.30. Have to study the sign of this. Okay, on the left-hand side, negative 10. Negative 10 plus 2, negative 10, so it's positive. On the right-hand side, I still have to discuss it here. I have to look at negative 1. Negative 1 plus 2 is positive, and this is negative. Now I'm plugging in 1, positive. I have to find this number here. So I have negative 1.3 minus 1 divided by 1.3 squared. Got negative 1.9. Now the moment of truth. I'm trying to see if these two work. If they don't, then I catch my mistake right now. Okay, from negative infinity to negative 1.9, definitely increasing. Yes. Negative infinity to negative 1.9 to negative infinity, definitely decreasing. From negative infinity to 0, definitely increasing. From 0 to infinity, definitely increasing. So I assume I'm correct. Now I have to find the second derivative. I'm going to use this to find the second derivative. That's the easiest form. So the second derivative will be negative 6 x to negative 4, which is negative 6 over x to the fourth. Very nice. Never 0 and always what type of sign? Always. Good. Ready? Let's graph. Any questions before we graph? I didn't mention anything about symmetry. It cannot be symmetric. It has a vertical asymptote at 0, but it crosses, it has a local max, I should say that. It has a local max here and no max here anywhere. So I would write that, you can write it here. F of negative x does not equal f of x, and it does not equal negative f of x, not symmetric. Okay, so let's see what we come up with. Here it is. A vertical asymptote x equals 0. A slant asymptote y equals x. And now negative 1.3, negative 1.9. Negative 1.3, negative 1.9. 1, 0. Okay, so let's read the chart. From approaching the slant asymptote at a negative infinity, the function is increasing to its local max. From approaching the slant asymptote at negative infinity, increasing to its local max. Opening downward. Now it's decreasing towards negative infinity, still opening downward. On the left-hand side of x equals 0, the vertical asymptote. On the right-hand side of the asymptote, it's coming from negative infinity, crossing the x-axis at 1, 0, opening downward. This is no point of max min because the derivative does not change sign or anything. 1 is not a critical number. There is no discussion there whatsoever. And now it's continued to increase towards infinity, opening downward and approaching the slant asymptote. I have to force it a little bit because there is nothing there. It's just a cross. Okay? So this is the function f of x, x to the third minus 1 over x squared. With the graphing calculator, the calculator would not show the slant asymptote. So don't forget parentheses, x to the third minus 1 parenthesis divided by, in parentheses, which you don't really need for the bottom, and y equals x. And now I'm going to use the standard viewing window. And here it comes. Turn, yes, yes. And now the slant asymptote is coming. Any questions? So what is different here? Just finding the slant asymptote. There is nothing else. Everything else is the same.
When do you do synthetic division and when do you make y equal x?
Very good. I do synthetic division when the denominator is like x plus or minus a number. So, for example, if I have x, oh yes, thank you. If I have, let's say, x squared plus x minus 7 divided by x minus 1, this function will have a slant asymptote because the top has degree 2 and the bottom has degree 1. And since the difference in degrees is 1 unit, the top is 1 unit higher than the degree of the bottom, this will have a slant asymptote. So now I can use synthetic division. I put in the box A. If I have positive 1, I put negative 1. But since I have minus 1, I will put only 1. Then the coefficient of x squared. Then the coefficient of x. There are no missing coefficients. If there is a missing coefficient, then I will put 0. I bring down 1. 1 times 1 is 1. I perform the operations I see. 1 times 2 is 2. And the remainder is negative 5. So therefore, this can be rewritten as, since degree 2 divided by degree 1 will give us degree 1, this is coefficient for x. This is the coefficient of the free term minus the remainder over the divisor. In this particular case, this is the slant asymptote. Any questions?
So it has to be changed by degree 1.
Yes. If I have this situation, this function does not have a slant asymptote because when you divide, you have to get a line. But if I divide degree 4 by degree 1, I get degree 3. Degree 3 is not a line. So if I have the top degree 6 and the bottom degree 5, when I divide, I get a line. So that's why the difference must be 1, so I can get a line. Anything else? Let's see if we have another couple of minutes to look at a word problem. Yes. What was that problem, Ben, with the pens and stuff like that? Was it a max-min problem?
That was trying to find the largest possible area using a limited amount of fencing.
And we were given the length, or?
The problem.
Okay, so we want to do something like that, or should I find something else? I'm looking on page 353. Yeah, let's do problem 50. Or at least start problem 50. On 353. Find two positive integers such that the sum of the first number. So can you give me two positive integers? Unknown. Well, x and y, right? Such that the sum of the first number and 4 times the second number is 1,000. The sum of the first number and 4 times the second number is 1,000. Very good. And the product of the numbers is as large as possible. So I'm asked to find the max product. How do I write the product of these numbers? What is the product of x and y? Good. Let's say I'm solving this equation because I have 3 variables. 1, 2, 3 variables. I can't. I'm going to solve for, let's say, for x, and replace it in here. And now this is a function of y. So negative 4y plus 1,000 times y. And you can say, I don't need calculus for this. I will have to agree. We did this in pre-calc. I do it in college algebra and intermediate algebra. But now we're going to use calculus. So I have a function, which is the product, and I want to find its maximum. Yes, you can say find negative b over 2a. And I'll say no, because I want to use calculus. What will you tell me to do then?
Differentiate.
Oh, of course. So find p prime of y, which is negative 8y plus 1,000. Okay, I have p prime. Now what do I do with it? No, because I'm not yet. I have to find the critical number first. I have to set it equal to 0. So I get y equals 1,000 divided by 8, which is what, 125? If x is 125, then how much? If y is 125, then how much is x? Negative 4 times 125 will be negative, what is it? 500, right? Plus 1,000 is 500. But I also have to convince you that y equals y equals 125 gives us a minimum. I'm sorry, maximum. I haven't convinced you yet. But in this, if I factor out negative 4y, right, I have y minus 200. No, 250, right? Okay. So when I plug in 0, I don't want to plug in 0. I want to plug in anything to the left of 125, like 100. If I plug in 100, this is negative, so this is positive. If I plug in 1,000, this will be positive, this will be negative. And now, yes. Now this is guaranteed to be a maximum because of the signs of the first derivative. So the maximum product, given the conditions that the sum of x plus 4 times y is 1,000, the maximum product will be 125 times 5. So max product is 62,500, given when x is 500 and y is 125. And I showed why 125 creates a maximum, because I studied the sign of the first derivative.